Hello. In this video, we're going to talk about a very important skill, which is manipulating equations to solve for a particular variable. In my classes, I've noticed a number of students have trouble when the variable is embedded in a more complex expression or if it's in the denominator or something. So we're going to go through the steps of how we go about manipulating these equations so that we are confident that we're solving for the right thing. In the previous problem, or in the previous video, we saw this equation, E is equal to hc over lambda, and we solved a pretty straightforward problem, which was solving for the energy when we were given Planck's constant, the speed of light, and the wavelength, and we focused mostly on the units there. In this video, what we're going to do is we're going to solve for lambda, the wavelength of light when we're given the energy h and c. So suppose we wanted to know lambda. That's the question. What is the wavelength associated with, in this case, a photon that has energy 1.234 times 10 to the minus 19 joules. So let's say that was given in the problem. Planck's constant is again 6.626 times 10 to the negative 34 joule seconds. So remember we have that two units on that particular number, and C is 2.998 times 10 to the 8 meters per second, or sometimes you'll see this written as meters per second, or sometimes you'll even see it written as meters seconds to the minus 1. All three mean the same thing. So part of being a good problem solver is simply decoding those kinds of things and writing them in ways that make sense to you. And that means practicing problems, quite honestly, and seeing which way you're comfortable doing things. Kind of like golfing, there are rules for good golf swings, but then you also have to just hit a lot of golf balls to get the feel for it. All right, so let's say we wanted to solve for the wavelength. Now we could put in numbers and gum things up, but sometimes I like to work with symbols because notice these are long numbers. It takes a long time to write out. So if I want to be an efficient problem solver, if I can just manipulate the symbols first and solve right away for wavelength and then put in the numbers, then we'll solve the problem more quickly. So I'm just going to rewrite E is equal to hc over lambda. We'll go through some steps. You might know how to do this, and if you do, great. This just serves as a refresher, but if it helps, consider what we'd want to do to get a wavelength isolated as the variable. We'd want to have an equation that ultimately just says wavelength is equal to something, and then be able to plug numbers into there. Well, if we don't know exactly how to do that, one thing we might do is multiply this side by wavelength. So what we would see is the wavelength there cancels. Now, you might remember from math classes that if we multiply one side of an equality by something, we also have to multiply the other side of that equality by the same thing. So we'd also have to multiply this side by wavelength. It's identical to saying something like 8 is equal to, 3 times 8 is equal to 24, something like that. Now, if I multiply both sides by, say, 4, if I just do one side, I no longer have an equality. But if I multiply this side by 4, I still maintain the equality. So anything we do to one side of the equation, we have to do to the other side of the equation. Nothing different when we're working with symbols. Again, so anytime we have a question about how to manipulate symbols, if we always go back to thinking about what we do with numbers, we can answer that question. Okay, so now in this case, we have lambda times energy is equal to hc. Well, we still haven't quite isolated the variable, but we do have lambda in the numerator now, which is good. So we need to get rid of the energy somehow. Well, in this case, we're going to divide by E. But if we divide one side of the equation by E, we have to divide the other side of the equation by E. The energy would cancel, and we'd have lambda is equal to hc over E. And now we know that we've isolated the thing that we're solving for, and we could go ahead and put numbers in. I do want to back up, though, and just point out that what has essentially happened if we started with E is equal to hc over lambda, what has essentially happened is the lambda came up and the energy went down into the denominator. So when they're on opposite sides of the equation, we could once we do this enough, kind of like golf again, or anything that's a hobby, once we do it a lot of times, we begin to see shortcuts and things. And so if you practice a lot of problems, you'll begin to see these little, they're not tricks, they're mathematical manipulations, but they become faster. Um, so we'll see that repeatedly, I think, in a couple more problems here. So we got there by simply doing multiplying both sides. There is another way to get there, which is we have E is equal to hc over lambda. Some of you might have thought, well, what if we take the reciprocal of this side? So if we turn the denominator into the numerator and the numerator into the denominator, that's called taking the reciprocal. If we do something to one side, we also have to do something to the other side. So we would have to take the reciprocal of the other side. So we'd have 1 over E now. Still have an isolated lambda, but to isolate lambda, we see that if we multiply both sides by hc, the hc's would cancel. So we end up with hc over E is equal to lambda if we go the route of taking reciprocals. So they all amount to the same thing. So whichever way you become most comfortable with getting these types of problems correct, I'd encourage you to go with. The important point in there is getting them correct and not guessing. So then at this point, we have that's solution. So now we could go ahead and plug in numbers. We said H is 6.626 times 10 to the negative 34 joules times seconds times 2.998 times 10 to the 8 meters per second, all over 1.234 times 10 to the minus 19 joules. This is getting a little crowded there. So I'm going to maybe switch pieces of paper and simply rewrite that. My apologies, but I want to make sure people can see this. And like I've done before, I'm going to convince myself that I have the correct units before I touch a calculator and try to get a number. I'm going to isolate the units. In terms of units, we have joule seconds coming from Planck's constant. We've got meters per second, and then all of that is over joules. Now notice in writing it as a fraction like this, it's easy to see that the seconds in the numerator cancels the seconds in the denominator of the numerator. So the numerator now becomes joules times meters over joules, because the joules in the denominator still carries over. Joules cancels joules, and we're going to be left with a wavelength in terms of meters. And then I asked myself, does that make sense? Well, a wavelength is in fact a distance. And if I measure distances in meters, that's good. I might be asked for this in centimeters or kilometers or something like that. But then I can always convert from meters into some other decimal system or into some other metric system measurement. So I'm just happy that I've ended up with units that reflect a length and not an energy or not seconds. I wouldn't want a time here because a wavelength is not a time. So if my manipulation led to seconds being the units, no matter what number I crank out in my calculator, it's not going to be correct. So the units are actually there to help us. I think sometimes we think of units as being oppressive, and they're not there to oppress us. They really are there to guide us. And now we can go ahead and calculate. So if we just take 6.626 times 10 to the negative 34, multiply by 2.998 times 10 to the 8, divide by 1.234 times 10 to the minus 19, we'd have a final answer of 1.61 times 10 to the minus 6. And our units are important here, right? Because if I say 1.61 times 10 to the minus 6, and that's it, you don't know if I'm talking about feet, inches, meters. Right? So we'd have to include the meters to get the whole thing correct. So again, if you have questions about those, I'd encourage you to contact me. I've put my email up a number of times. I'm going to move on to some other ideas. Suppose in the following that we wanted to solve for the variable z2. So we're going to abstract this a little bit where we don't have numbers anymore. And let's say we had an equation that was x to the fourth, y to the fifth over 37 is equal to 29 times the square root of t divided by z sub 2. All right, so z sub 2 is just a variable. The 2 is just there to denote that it's different from z1. It's not a squared. It's not something like a fourth or the fifth. So again, part of the skill in general chemistry and biology and math is really getting a handle on symbols and squaring, and I shouldn't say squaring away, figuring out what symbols mean and why we're using subscripts and superscripts and the like. Okay. So let's say we wanted to solve this for Z2. Well, again, lots of different ways to do it. You could think about taking the reciprocal, and if we took the reciprocal of this side, we'd have to take the reciprocal of the other side. I always think of this as in terms of moving the z squared over to the other side of the equal sign, which, as I showed before, really amounts to multiplying both sides by z2. So we get z2 times x to the fourth times y to the fifth over 37 is equal to 29 times the square root of t. And then in this case, the z2's would cancel, which is why we multiplied by z2 in the first place. Key thing here again is anything we do to one side of the equation, we have to do to the other side of the equation. Otherwise, we ruin the equality. If I say 8 is equal to 4 times 2, I have a true statement. But if I just come along and multiply this side by 3, then I say 24 is equal to 8, and that's nonsense. But if I multiply this side by 3 as well, well, now I'm back into having a valid equality. Doing exactly the same thing with symbols. Want to isolate for Z2, so it looks like now we go back to our previous skills of just looking at fractions. If I want to kind of clear the 37, I would multiply by 37. That's going to get that to cancel, and we would divide by x to the fourth, y to the fifth. So we're going to do that to this side. That would get all of those things to cancel and isolate Z2, but that means we also have to multiply this side by the same thing. So this side ultimately becomes 29 times the square root of t times 37 over x to the fourth times y to the fifth. We don't have to know what x is. We don't have to know what y is in this case or t. We're just manipulating symbols. But again, if we're talking about chemical equations, these kinds of manipulations are necessary and helpful to know. And if we don't like dealing with symbols, again, we can always make analogies to what we might do, or if we shouldn't say we might not like symbols, but if we were confused or initially didn't know how to proceed, just stick numbers in. Use numbers to represent groups of symbols. So I'm just going to say this is 5 times 9 over 37, and this is equal to 29 times the square root of 18 over Z2. And how would I handle that if I were asked to solve just algebraically for Z2? Well, I'd do exactly the same thing. I would multiply this side by Z2 and multiply that side by Z2. So we'd have Z2, and then we would multiply. So notice I'm going to try to speed things up here. This is part of becoming an efficient problem solver. I know that I'm going to multiply this side by the reciprocal of what I see here. So I'll just save a step and go ahead and multiply by the reciprocal there and just immediately go to that. And now we can go back to what was 29. Well, 29 was 29. This was the square root of t. So we could say that. And then the 37 was, in fact, the 37 in the denominator. 5 represented x to the fourth. 9 represented y to the fifth. So now in terms of the symbols that we were originally given, we'd be back to Z2 is equal to 29 times the square root of t times 37 over x to the fourth, y to the fifth, which is exactly what we got when we did the symbolic manipulation. So if you're comfortable using numbers, which I hope you are, then use that to your benefit when we give you symbols, or when life gives you symbols, turn them into numbers and see if that helps. One last then logic extension from that. And what I'm going to do is put this problem up and give you a moment to pause the video and try this problem. So we're going to have the at times pound or hashtag over $ squared is equal to percent times y over toothbrush. Totally nonsensical, but now what I'd like you to do is pause the video and solve for $. Okay, I hope you've pushed all the way to the end to solve for $. I think it's important that we always commit to an answer so that we can honestly say, did I get the whole thing right or did I miss something? And if I miss something, be honest about that to ourselves and not just say, oh, I made a simple little mistake. I hear a lot of students doing that. And a lot of times the mistakes aren't silly or simple, they represent a misunderstanding. So they're an opportunity to learn. So in this case, again, we could think of this as either way. I'm going to go ahead and say, let's do the reciprocal of both sides. So if I turn one side upside down, I turn the other side upside down. This amounts to multiplying this side by $ squared and this side by $ squared. Notice the dollar signs would cancel. We'll get to the same point. We'd have $ squared. And then to isolate $, we're going to take $ squared. I'm going to multiply both sides by at hashtag. So at hashtag toothbrush over percent times y, which is where we would get if we stuck with multiplying both sides by $ squared, and then we'd have to multiply by toothbrush, divide by percent times y. So either way you did it is perfectly fine if you got to this step. And now the last step is if we wanted to just get $ and not $ squared, what do? Well, we'd have to take the square root of both sides. Well, the square root of $ squared is just $, and then that leaves us the square root of at hashtag toothbrush over percent times y. So we have symbolically manipulated and solved for $. So the last thing we're going to do here is one of the more complex equations that we'll see in general chemistry in the first semester. One that troubles a lot of students. It's actually one of my favorite ones because I'm filming this actually pretty shortly after July 4th. In fact, it's just July 8th. So this equation actually helps us predict the wavelengths of light that would be emitted by hydrogen. So when we blow up a firework, what we're really seeing is light being emitted by different atoms. So if that atom were hydrogen, this equation would tell us which wavelengths we would see, whether it would be green or yellow or red or into the ultraviolet or infrared regions. So it's one of my favorite equations just because it's kind of neat. Okay, so let's say here that we wanted to solve for y squared. Okay, where do we begin? It's a bit more complicated because now we have addition and subtraction and things like that. I'm first going to solve a problem related to this, but instead of all these symbols, I'm just going to put in numbers. Okay, so we're going to again go back to, can I solve this with numbers? If I can't solve this with numbers, I'm probably not going to be able to do it with symbols. So if I needed to solve for y here, and I didn't just want to plug it into my calculator, but I actually wanted or needed to manipulate this, we start seeing a couple things. The first thing that might pop out to you is that we might want to deal with this 7. We could divide both sides by 7. So I'm going to say we're going to divide this side by 7, and we're going to divide that side by 7. So now on this side, we have a complex fraction. We have 1/6 in the numerator divided by 7. But the nice thing is that that 7 cancels. So this side becomes 1/5 minus y squared. We saw in earlier videos that to get rid of this complex fraction, it would be nice if we can turn the denominator into 1. Well, how do we turn the denominator into 1? Well, if we multiply the denominator here by 1/7, that would turn the denominator into 1. But if we do that, we need to multiply the numerator by 1/7. So again, that we're just multiplying by something that's equal to 1. So we're not actually changing this side, because if we change the numeric value of this side, then it would no longer be equal to the numeric value of that side. So this equal sign is really important. We're doing everything in our power to keep those two sides equal. That's what the whole thing starts out. That's the premise of the whole equation. Now we would have 1 over 42, or actually I'm just going to leave it as 1 over 6 times 7, since we're using those as placeholders for symbols, over 1, right, which we now know is 1 divided by 6.7, 6 times 7. And that's equal to 1/5 minus 1 over y squared. So now we want to isolate y squared. Well, that says we got to get rid of this on this side. So how are we going to get rid of a positive 1/5 on that side? Right, we got to subtract 1/5. So we're going to subtract a fifth from that side. Well, if we subtract a fifth from this side, we have to subtract a fifth from this side. So we're going to have 1 over 6 times 7 minus 1/5 is equal to minus 1 over y squared. Now here's a situation where I see a lot of students going, oh, it's a negative sign. I'm just going to ignore it because I don't like negative signs. So let's just hope it goes away, and I'm going to rewrite this without the negative sign. As soon as you feel that in your gut where you know you're doing something that probably isn't right, you're probably not. So let's just deal with that negative sign. How do we get rid of a negative sign? Well, we're going to multiply this side by -1, which means we have to multiply that entire side by -1. Not just one of these terms, but the entire side needs to get multiplied by -1. So now we're going to have -1 over 6 times 7. The negative comes through and we get positive 1/5 is equal to 1 over y squared. We still haven't isolated y yet. Y is in the denominator. So now you might think, oh, well, I'm just going to take the reciprocal, right? So if I take the reciprocal of this side, I'd have y squared, and then I'm going to take the reciprocal of this side. And this is going to hurt me to write, but I'm going to write it because I see it written a lot by students. And, oh, I'm just going to turn this into 6 times 7, and there's a negative sign out here, so I'll do that. And now I've taken the reciprocal, so I took the reciprocal of this, the reciprocal of that, and the reciprocal of that. Okay. That doesn't work. And I want to show you why it doesn't work. And here again, we can convince ourselves of the mathematical manipulations we're about to do. So let's say we had 1/2 minus 1/8, and that is equal to 3/8. Okay. You can check that. You can take out a calculator, calculate this side, calculate that side, and I guarantee you that you will find that 1/2 minus 1/8 is in fact equal to 3/8. If you really want to be convinced of that, 1/2 is the same thing as 4/8. 4/8 minus 1/8 is equal to 3/8. So now if we go back to what I just tried to do that I said is incorrect, I'm going to take the reciprocal of this side. That means I'm going to take the reciprocal of 1 over 2, which would be 2 over 1, minus the reciprocal of this, which would be 8 over 1. And now we get the statement 2 minus 8 is equal to 8/3. And we have to ask ourselves, is that correct? Well, clearly not. 2 minus 8 is -6. -6 is not 8 over 3. Okay. So we've just convinced ourselves that when we get to this point, we cannot merely take the reciprocal by taking in the reciprocal of all three terms. It doesn't work because this is not multiplication, it is addition. So how are we going to handle that? Well, I'm going to rewrite what we had before. We had 1 over 6 times 7 minus 1/5 is equal to 1 over y squared is where we had gotten. What we need to do now is put all of these things over, I'm sorry, this should be a positive sign. put these things over a common denominator. Well, how do we find a common denominator? We've got 6 times 7 over here. We've got 5 down there. If you remember, then common denominator, we're going to multiply this fraction by 5 over 5, and we're going to multiply this fraction by 6 times 7, and this fraction by the numerator and the denominator by 6 times 7. So this becomes minus 5 over 5 times 6 times 7 plus 6 times 7 over 5 times 6 times 7. And now that's equal to 1 over y squared. So we do have, in fact, a common denominator. Now we can combine these two terms. So we have minus 5 plus 6 times 7 over 5 times 6 times 7 is equal to 1 over y squared. And now we can take the reciprocal of both sides. 5 times 6 times 7 over minus 5 plus 6 times 7 is equal to y squared. So we take the reciprocal of this side. We take the reciprocal of that side. And then to get rid of the y squared, we would just take the square root of both sides. So we would end up with the square root of 5 times 6 times 7 over negative 5 plus 6 times 7. And if we go back to our original equation, let's see if I can find it. 6 stood in for wavelength, 7 stood in for r, 5 stood in for x. So 5 stood in for x, 6 stood in for r, 7 stood in for wavelength, minus 5, which was minus x, plus 6 was wavelength times r, so we'd get the square root of that. Sorry. That should be wavelength. That should be x. That's wavelength, lambda symbol. Okay. So that's using numbers to do this. Let's see where we end up if we go back to using symbols. Again, if you, I'm going through this relatively quickly. If there are steps in there that you want to review, I'd encourage you to just pause the video, go back to those steps, and take a look at those. Use this as a learning opportunity. So now we're going to manipulate the symbols. We're going to basically do the same thing. Divide both sides by r. Or if we want to, we could think of this as multiplying by 1 over r. So if we multiply that by 1 over r, we get 1 over r times lambda is equal to 1 over x squared minus 1 over y squared. Saw that we had to bring this over as a negative. We subtract. From both sides. Still have our negative sign out there. That's another important thing, that the negative sign modifies that minus 1 over y squared, so we need to retain it. Now we want to get rid of it by multiplying through by a negative. So we have negative 1 over r lambda plus 1 over x squared is equal to 1 over y squared. And here, again, we can't just take the reciprocal. We prove that to ourselves. So we might be stumped. Go back to numbers here and say, what would I do with numbers? If you're working on homework. You know, there's a great line. My wife really likes the line from Apollo 13 where they say, don't make the problem worse by guessing. So if you find yourself guessing, that's a good time to pause and say, no, I really want to make sure I get this right. So we find a common denominator. Common denominator is going to be x squared r lambda. So that means we have to multiply this by x squared. We have to multiply this by r lambda. So this now becomes minus x squared plus r lambda over x squared times r times lambda is equal to 1 over y squared. Finally, take the reciprocal, we get x squared r lambda over minus x squared plus r lambda is equal to y squared, and then we take the square root, x squared r lambda over minus x squared plus r times lambda. which does match what we had before when we used our substitutions. Now I had left out, when we used numbers, I had left out squares and things like that. So not entirely analogous, but that would be the manipulation there, and all that would be equal to y. Now, if we had numbers for x and r and lambda, we could plug them in and just do a single calculation rather than trying to do the whole manipulation carrying along a bunch of numbers. So I would encourage you to review this. If you have questions, send me an email. Again, I will write down my email address, mark.vaitha@drake.edu. And there'll be some problems related to this kind of manipulation, as I've mentioned in other videos. So I hope you use this and work with it. Just like learning a sport or a musical instrument, it takes practice. So have a good afternoon, or whatever time of the day you're watching this. Enjoy the rest of your day. Thanks.